Hi, Assalamualaikum and a very good morning. Okay, so we continue our lecture, which is chapter Saturn, okay, after Jupiter. Okay, so we will learn in this chapter about the orbital physical properties, the Saturn atmosphere, interior and the magnetosphere, okay, and then the Saturn spectacular ring system, and also the moon of the Saturn. Okay, now the introduction of this chapter for Saturn. Okay, so Saturn is one of the most beautiful and enchanting of the all astronomical objects. Okay, as we can see in this figure, very huge and nice planet. Okay, the most beautiful planet in the all astronomical object, and best known feature, okay, its rings, okay, and was the most outermost planet known to ancient astronomers, and named after the father of Jupiter in Roman mythology. Okay, so now we go to the overall properties of the Saturn. So Saturn orbits the Sun almost twice the distance of Jupiter. And the sidereal orbital period is 29.4 years. Okay, was the longest natural unit of time known to the ancient world, and its mass about 5.7 times 10 power of 26 kg. Okay, and long before the arrival of the spacecraft. And the Saturn's equatorial radius is 60,000 kilometer, and the average density is 700, okay, and indicating that it is composed primarily of hydrogen and helium, yet less compressed than Jupiter due to lower mass. Okay, how about the rotation rate? Okay, so the rotation rate is very rapidly and differentially. Okay, the atmospheric rotation period is 10 hours, 14 minutes at the equator, and determined by tracking weather feature observed in the planet's atmosphere. So the rotational period of the interior is 10 hours, okay, measured via magnetosphere outburst. So the Saturn's axis of rotation is tilted at 27 degree to the planet's orbital plane, and this Saturn rapid rotation makes it the flattest planet in the solar system. Okay, with a polar radius is just 54,000 kilometers. And the degree of flattening is less than what is expected for a composed of hydrogen and helium alone, therefore suggesting a rocky core, okay, about 1.5 times the mass of Jupiter's core. Okay, so we go to the rings system of the Saturn. It lies in its equatorial plane. Okay, so its appearance changes as Saturn orbits the Sun. Okay, so the appearance can be will be changed, okay, due to the orbit to the Sun. So it's the highly reflect but these regions displays no significant atmospheric structure. Okay, so this image is taken by Cassini in 2005. It is a mosaic of get 100 photographs taken in true color. So the highest resolution global image ever made of Saturn. Okay, the composition and coloration. Composition of Saturn's atmosphere was difficult to detect since in Saturn's cold upper atmosphere, most molecules are in solid or liquid form, with relatively little of it present as a gas to absorb sunlight and create spectral lines. So this is the atmospheric composition of the Saturn. Okay, as you can see, divided into four: hydrogen, helium, methane, and ammonia with a different percentage of composition. Okay, so the fraction of helium, okay, is far less than it observed on Jupiter or in the Sun, suggesting that at some time in Saturn's past, the heavier helium began to sink towards Saturn's center and reducing its abundance in the outer layers. So the Saturn likes a solid surface. We take the top of the troposphere as our reference level and set it to 0 kilometer. The top of the visible clouds lie about 50 kilometer below this level. Okay, the clouds are arranged in three distinct layers composed of ammonia, ammonium hydrosulfide, and water ice. Okay, so above the cloud lies a layer of haze formed by the action of sunlight on Saturn's upper atmosphere. Okay, so the total thickness okay, of these three cloud layers is roughly 200 kilometer, much thicker than Jupiter, which is 80 kilometer because of its weaker gravity. The colors of Saturn's cloud layers are due to the same basic cloud chemistry as on Jupiter, but due to the thicker clouds and fewer holes and gaps in the top layers, we only see the overall butterscotch hue. Okay. Okay, how about the weather? In the Saturn, overall stable east-west zonal flow. Okay, zonal flow means the east-west direction. East-west here. Okay, if we can zoom in this area. So we got this. Okay, the structure. Okay, and it's also reflected the weather. Computer enhanced here. They clearly show the existence of bands, oval storm system, and turbulent flow patterns. Okay, the large-scale flows here, you can see the wind speed powered by the convective motion in Saturn's interior and by the planet's rapid rotation. So here is eastward wind with the variability with their latitude. Okay, this is from the equator in the middle. And then when going to the positive side of latitude, increase will be like this. And negative side for the latitude, it will be like this. So the eastward is varies with their latitude. So in the equator, we can see the wind speed is very high. Okay. So the zonal flow on Saturn is considerably faster than on Jupiter. So the equatorial eastward jet stream move at a brisk 1,500 km per hour and extends to much higher latitudes. For latitude 14 north, okay, marks the strongest band on Saturn and the most obvious ovals and turbulent eddies. Okay, at the 40 degree. Okay, at the 40° north. Okay, in September 1990, American astronomers detected a large white spot just above Saturn's equator. Hubble Space Telescope imaged the phenomenon. So the spot developed into a band, clouds completely encircling the planet's equator, as we can see in this area. Okay. So this white coloration may have arose from crystals of ammonia ice formed when upwelling plume of warm gas penetrate the cool upper cloud layers. Okay, here. So the large white spots are relatively rare on Saturn. They appear roughly every 30 years during northern summer. And the Cassini measured strong bursts of radio wave from a large and complex storm in late 2010, most likely produced by intense lightning discharge below, powered by convection and precipitation. Okay, means the water and ammonia rain. Okay, this is the ring, ring of the Saturn. Okay, clouds feature here. And also the crystal of ammonia ice. Okay. So this Cassidy has also detected numerous small dark storms. Okay. And providing a means for energy to flow from Saturn's warm interior into the cold atmosphere. Okay, this is the interior of the Saturn, okay, which captured by using the spacecraft observation, okay, and theoretical modeling. So you can see the molecular hydrogen, metallic hydrogen in this layer, and also the different depth of the interior of Saturn. Okay, there is also the metallic hydrogen in thinner, and its core is larger of metallic hydrogen. Due to the lower mass, Saturn has a less extreme core temperature and density. Okay, its pressure is 1/5 of Jupiter. So the surface temperature is -176°. Okay, and it radiates about 3 times more energy than it absorbs. So suggesting it has internal energy source. Okay, it's also lower internal temperature, doesn't allow helium to dissolve so easily. And it's probably started out with a fairly uniform solution of helium dissolved in hydrogen, but the helium condensed out of the surrounding hydrogen, and the amount was greatest in its cool outer layer, where it turned into continuous helium shower. And this helium precipitation is responsible for depleting the outer layers of the helium content. Okay, the internal heating continue. Okay, for gravitational energy, which releases the source of Saturn's internal heat. Okay, and okay, this is the cool version of the temperature. Okay, so now we go to the magnetospheric activity. Saturn's electrically conducting interior and rapid rotation produce a strong magnetic field and extensive magnetosphere. Okay, about 1/20, 1/20 the strength of Jupiter. And the Saturn magnetosphere is not inclined with respect to its axis of rotation, but like Jupiter, it is oriented opposite that of the Earth. Aurora also can be seen, okay, can be observed on Saturn here in the North and South Pole. Okay, so for the Saturn's magnetosphere extend about 1 million kilometer toward the Sun, okay, and it has 16 small moons in the inner part, with Titan is the largest moon, okay, and occasionally inside of it depending on the intensity of the solar wind. No major moons, okay, lie deep within Saturn atmosphere. Therefore, it does not have a plasma torus. The radio wave it emits can only be detected through the space-bound observation. Okay, the planetary ring system, okay, was the first observed by Galileo, okay, but he thought it was part of a triple planet of some sort. Okay, if you can see A, B, C, okay, from this to this figure, and then got the idea of the Saturn's feature. Okay, and it's now in 1616, Galileo realized that the bumps were elliptical in shape. Okay, in figure B, and the Dutch astronomers Christian Huygens realized the bumps were a thin and flat ring completely encircling the planet after so many years. Okay, they got the idea. And then the Italian astronomer Giovanni Domenico Cassini discovered a dark band, okay, looks like a gap between the ring. Okay, so it is now known as the Cassini division because of the finding of this guy. The three inner visible rings are called C, B, and A. Okay, A, B, C. Okay, so C, B, A. C, B, A rings. Cassini division lies between the B and A ring. Okay, so the main item is the B and A ring, and this B and A ring divided into the C, B, A rings in the middle. Okay, this is the view from Earth. Okay, the much narrower gap is found outside the A ring. Okay, this is the details of value of the parameter of the ring in terms of the brightness, BAC. Okay. Okay, so what are Saturn's rings? Okay, the various dynamic and thermodynamic argument had conclusively proved that the ring could not be solid, liquid, or gas. Okay, a solid ring will become unstable and break up. The rings are composed of a great number of small water ice particles, all independently orbiting Saturn and reflecting about more than 80% of sunlight. So the rings are thin, 10 to 15 meter, because the collision between ring particles tend to keep them all moving in circular orbit in a single plane, and a symmetric gravitational field of Saturn due to the flattened shape makes the ring lie in the planet's equatorial plane. Okay, the Roche limit. When we bring a moon close to a planet, the tidal force on it increases, okay, creating a tidal patch. As the moon gets closer and closer, it reaches a point where the tidal force becomes greater than the internal force holding it together, which causes the moon to be torn apart. And the third one is the pieces of the satellite then pursue their own individual orbits around the planet, eventually spreading all the way around it in the form of a ring. Okay, so the Roche limit is the name after the French, okay, mathematical Edward Roche, because it gives uh, the theoretical version of the explanation about the ring system. Okay, so this is the assumption of this Roche limit. Okay. Okay, so for Saturn, no moon can survive within a distance of 15144 kilometer of the planet center, which is 7,000 kilometers beyond the outer edge of the A ring. And all major planetary rings are found within the Roche limit of their parent planet. However, sufficiently small moons can survive within the Roche limit because they are held together mostly by interatomic forces. Okay, we can see Jupiter, Saturn, Uranus, Neptune, the difference in their planet radius and the division of their feature, okay, in the surface. Okay, if Jupiter, we can see the Roche limit is here. Okay, in the similar radius of these 4 different planets. Okay, so the rings in detail. Okay, we have the Voyager, okay, and Cassini. However, reveal the rings to be vastly more complex than we imagine. So the main rings are actually composed of 10,000 narrow ringlets. Okay, so the comparison of our Earth and just the ring of the Saturn, so it's very big and wide planet, okay, compared to us. So the ringlets are actually not separated from one another by empty space, but it contains concentric regions and alternating high and low concentration of ring particles. And also have a wave of matter. Is the gravitational influence of Saturn in the moons and the mutual gravitational attraction of the ring particles, okay, to form and move in the plane of the ring and forming tightly wound spiral pattern, which is spiral density wave. And 20 narrow gaps are thought to be kept clear by the action of the small moonlets, okay, embedded in them, which sweep up ring material through collision as they go. So the rings in details is 2 notable ring shapes in the gaps, okay, which is Pan and Daphnis. Okay, so it's formed by the Voyager 2, okay, and known as the collectively as the D ring inside the inner edge of the C ring, stretching down almost to Saturn's cloud tops. And 2 other fan rings, the G and E rings, were later discovered with the E ring associated with volcanism on the moon and Enceladus. The fan ring can be better seen behind the planet, looking back toward the eclipsed sun. Okay, this is the Enceladus from the ring that they discovered along the time. Okay, so this one, the moon is reflect or associated with the volcanism in the G and E rings. Okay. Okay, I think we stop here and we continue in the next video. Thank you.